Welcome back. Today we're jumping right into another explainer, and we're looking at the absolute unsung heroes of the mobile network. You know, when you pull out your phone to instantly load a web page or make a call, you probably just thank that cell tower down the street, right? But honestly, there's an entire, massive, completely hidden infrastructure that actually keeps that tower alive. So today, we're focusing squarely on the field engineers. These are the professionals who literally battle the elements to keep our world connected.
Okay, let's dive into this core part of the network. What exactly are we talking about here? Well, we're defining what's called the transport network, or as it's more widely known in the industry, the backhaul. Basically, it's a critical, invisible bridge. Think of this bridge as the vital lifeline connecting those standard street cell towers you see every single day to the main core exchange building. Without this invisible connection, that tower, it's completely isolated, useless, really.
So, to really grasp how this all works and, how it inevitably breaks, here's our roadmap for today. We'll start with the invisible bridge, then compare fiber versus microwave, look at microwave misalignment, tackle the fiber cut, examine the rain fade challenge, and finally wrap up with the transport checklist.
All right, Section 1, the invisible bridge.
Think of this cell tower like an airport for passengers and cargo, but in this case, obviously it's your data. Now, the backhaul is the invisible highway that actually transports all those passengers and cargo into the main city. It's an incredible system, but here's the catch. If this invisible highway collapses, the airport basically drops completely off the map. It completely loses its connection to the outside world, no matter how perfectly functional the tower itself might be. So it begs the question, how do we actually build this highway?
Let's get into Section 2, Fiber versus Microwave.
And this brilliantly illustrates the two main physical mediums we use to pull this off. First up, we've got fiber optics. These are thick, underground cables carrying massive amounts of data using pulses of light. They're the absolute standard for high-traffic city environments. Then, on the flip side, we have microwave links. You've probably seen these. They're those round white dishes mounted super high up on towers. They literally shoot data through the air using radio beams. They're just the perfect solution for remote mountains, deserts, and rural areas where, frankly, digging deep underground trenches for fiber is just impossible. But, as we all know, out in the real world, things go wrong.
Which brings us to Section 3, Microwave Misalignment. Picture this. You're monitoring the network, taking a sip of coffee, and suddenly your dashboard flashes red alarm, link down, high bit error rate. Total panic mode, right? So what just happened? Well, a heavy storm probably just rolled through. You see, microwave dishes have to look directly at each other with absolutely perfect line of sight. When strong storm winds hit the tower, the physical bracket can actually loosen, causing the dish to shift by just a few tiny millimeters. And get this, that microscopic shift is enough to completely drop the signal. Crazy, right?
So the alarm is blaring, but the fix? It requires calm, deliberate action. First things first, you've got to put on your climbing gear and physically scale that tower. Second, you whip out your multimeter tool and deliberately measure the received signal level, or RSL. What you're doing is hunting for that absolute perfect target decibel level, and once you finally find it, step 3, you firmly lock those bracket bolts right back into place so the wind can't mess with it again. Problem solved. But wind isn't the only threat out there.
Moving on to Section 4, the fiber cut.
So the crucial point here is understanding the sheer, utter dread of seeing a critical alarm pop up, loss of signal, or LOS, detected on the underground fiber. We call this the construction trap. Basically, somewhere out in the city, an excavator or a road crew has accidentally sliced right through the underground fiber optic cable that feeds your tower. Think about the frustration of a backhoe operator taking down a whole city block's internet in a single scoop. It happens. The invisible highway bridge has literally collapsed.
Now, you obviously can't just dig up miles and miles of road looking for the break. That'd take forever. Instead, you need the OTDR, which stands for Optical Time Domain Reflectometer. I like to think of the OTDR as the engineer's ultimate radar. It's this brilliant smart device that actually shoots light directly down the broken fiber underground. Then, it measures the reflection and tells you the exact distance to the cut, literally down to the meter. It's how you find the needle in the haystack buried beneath the city streets.
Okay, so once you have your distance, here's the action plan. Step 1, deploy that OTDR. Step 2, you drive out and locate the exact street excavation site where the accident happened. And then step 3, the actual physical repair. The engineering team has to bring in a highly specialized fusion splicing machine,
Watch this. They literally melt the broken strands of glass fibers back together to permanently restore the link. It's incredibly precise, delicate work, usually happening right on the side of a chaotic, noisy road. So we've battled the wind, and we've battled the excavators. What's next?
Let's look at Section 5, Rain Fade Challenge.
This brings us to a really fascinating technical dilemma. How on earth do you fix a microwave link when heavy rain is physically absorbing the radio energy? You see, high-frequency microwave links really suffer in heavy rain or dense fog. The physical water drops in the air actually scatter the beam. They absorb the energy, which causes all these dropped data packets across the network. Now, you can't exactly stop the rain, right? But what you can do is configure the system to use something called adaptive modulation. Let's move to and see how this builds into an awesome solution. It's an automatic system configuration. Basically, when heavy rain starts hitting the beam, the system intelligently and automatically lowers its transmission speed. By pacing the data and slowing things down just a bit, it keeps the connection stable instead of dropping the link entirely. It's a brilliant trade-off. You're sacrificing top speed for absolute reliability during the storm.
And that brings us to our final part, Section 6, the transport checklist.
Now, what's really interesting about this slide is it gives us our ultimate field readiness checklist. Because if you're managing the backhaul, you are the one keeping the highway clear. So here's what you need. Number 1, always check and lock those microwave mounting brackets. Number 2, never leave for the field without a clean OTDR and spare optical patch cords. Seriously, don't forget them. And number 3, proactively monitor those RSL levels before and after heavy storms. That way, you can catch a misalignment before it ever triggers a critical alarm.
And you've always got to remember the golden rule out in the field. Your speed saves the network. Keep the data flowing. Because honestly, whether you're hundreds of feet up in the air aligning a heavy microwave dish in howling wind, or you're standing in a muddy trench tracking a cut fiber down a city street, it's the field engineer's physical and technical heroics that truly keep our modern world moving. The invisible highway relies entirely on you. So the question is, will you be ready to keep the data flowing when that next critical alarm hits? I know I'll be thinking about it. Next time you load a video on your phone during a massive rainstorm, just take a brief moment to appreciate the unseen engineering battles being fought every single day just to make that connection possible. Thanks so much for joining me on this explainer, and I'll catch you in the next one.